This set of slides talks about boiling and boiling points and how we can compare boiling points and atmospheric pressure and how we can throw intermolecular force knowledge into that to help us figure out the temperature at which something is going to boil. So just boiling is a conversion of liquid to vapor within a liquid as well as on its surface. So if we remember the difference between evaporation and boiling, we know that evaporation is from the surface of a non-boiling liquid, and that boiling is the conversion of a liquid to a vapor within the liquid as well as on its surface. And boiling occurs when the equilibrium vapor pressure is equal to the atmospheric pressure. Boiling point is the temperature where the equilibrium vapor pressure of the liquid is exactly the ambient atmospheric pressure. So essentially, it's equal to the pressure acting on the surface by the atmosphere. So when we talk about boiling point, we do need to take into account the intermolecular forces present in the liquid, but we also need to take into account the amount of energy that needs to be overcome due to the pressure pushing down on the surface of that liquid. So when we talk about elevation, we actually will talk about how elevation can affect the boiling point because the atmospheric pressure pushing down on that liquid will vary. So again, the boiling point is the temperature where the equilibrium vapor pressure of the liquid is exactly equal to the ambient atmospheric pressure. So it's essentially, we can talk about those energies being equal so those molecules now can get into the gas phase. So at sea level, the temperature at which the vapor pressure is 1 atmosphere, the boiling point is 100 degrees Celsius for water. And again, most of the time we'll talk about water in this unit, but understand it's not 100 degrees Celsius for all liquids, just for water. So at this point, at 1 atmosphere, at 100 degrees Celsius, the bubbles of vapor can form within the bulk of the liquid. So there is enough energy now within that liquid, if we're heating it, to be able to form bubbles. So the molecules of gas are not just coming from the surface, but from everywhere. And this is just, again, a good reminder that boiling happens from the whole body of liquid rather than just from the surface. And there's energy included everywhere, not just the molecules at the surface getting enough kinetic energy to escape the surface of that gas if we're talking about evaporation. So normal boiling points refer to standard pressure, which is 1 atmosphere. So if the atmospheric pressure increases, the vapor pressure must increase for the boiling point to be reached. So that just means the molecules that are going to be into the gas phase must increase. So this requires an increase in temperature. So if I were to put more force on the top of a liquid, then I would need to increase my vapor pressure to reach that equilibrium so that I can have that liquid boil. If the atmospheric pressure decreases, then the vapor pressure must decrease for the boiling point to be reached, and thus this requires a lower temperature. And so, since boiling point occurs at a lower temperature, it would take longer to cook at high altitudes. So if you think about it, if we boil water in the mountains, it might only boil at 93 degrees Celsius, and that's an arbitrary term. I made that up just so that we have an example, and a value. So if it only boils at 93 degrees Celsius, it means it would boil faster because it doesn't take as much energy to get to 93 degrees Celsius as it does to get to 100 degrees Celsius. But it means that my 93 degrees Celsius water is not as hot, it does not have as much kinetic energy, it does not have as much energy stored, so I would need to cook things longer at higher altitudes. And that's why if you have a cabin, or if you have been to the mountains and done some cooking and you see on box labels where it says if you're at an altitude you need to bake this or cook this for longer, this is essentially the reason why. So again, if I'm at sea level, then I know that the pressure is going to be much greater than if I'm in the mountains, and so the boiling point is higher because the energy required to overcome the pressure is greater. So if I'm in the mountains, the pressure pushing down on the liquids is lower, and so the boiling point is lower because there's less pressure to overcome. So it's going to boil faster, but it's going to boil at a lower temperature. So here's just an example. Again, arbitrary numbers, but hopefully understanding the atmospheric pressure differences and the boiling point differences due to those changes in atmospheric pressure. So here's a graph that we can actually look at and identify different liquids and at different pressures what their boiling point is going to be. So we can look at the pressures, which are along the outside right here, and we can look at the temperatures, with which they are going to boil. And so let's say at 200 degrees, or at 200 millimeters of mercury, at 400 millimeters of mercury, and 600 millimeters of mercury, where are these things going to boil? So at 200 millimeters of mercury, I know that diethyl ether will boil around maybe 1 degree Celsius. At 400 millimeters of mercury, ethanol will boil around 65 degrees Celsius. At 600 millimeters of mercury, water would boil maybe around 95 degrees Celsius. So again, maybe this is like Stanley in the mountains in Redfish Lake area, one of my favorite places to go. So maybe it's going to boil faster because it only has to get to 95 degrees Celsius, but again, you're going to have to boil it longer. We can also use this graph to predict intermolecular force strengths within the molecules. And so if I'm looking at 200 millimeters of mercury, diethyl ether maybe boil at 5 degrees Celsius or 1 degree Celsius, something like that. Ethanol might boil at 48 degrees Celsius. Water might boil at 63 degrees Celsius. And so the lower the boiling point, the weaker the intermolecular forces. And so I can even just look, I don't even need to compare it to atmospheres. If I just look at this, I could say diethyl ether has the lowest intermolecular forces because it clearly has the lowest boiling point of any of those molecules. And ethanol would be second, and then water would have the highest intermolecular forces. So we can also use the graph to predict that if it's got a higher boiling point, it's probably got stronger intermolecular forces. Just again, another graph, we can look at boiling point versus vapor pressure and atmospheric pressure, and then also we can predict intermolecular force strength. And we'll use these graphs to answer some analysis questions on our lab on block day, so now you know how to use them.